Okay, thank you, Charles. Appreciate the introduction, and this has been a really fun visit so far. So I really want to compliment the organizers and the Molecule Maker Lab Institute for their vision. So it's unlike a usual sort of seminar invitation. I think it's really impressive, the vision that the Institute has, and I think a lot of people are thinking about automation and science, and it's neat to be at a meeting where there's such a high density of people contributing to this. So my contribution here is I'm giving you a fresh talk. So I've never given this particular presentation before, and I'm introducing it with a question, okay? So this isn't an idle question. This is a serious question. So where's the prediction frontier in materials chemistry? So the flippant response is, who knows? It's changing every day. But actually the serious response is also, it's changing every day. So if you look at, if I look back at my career through my training, the pace of shifting frontier for prediction was extremely, extremely slow. Okay, so when I say prediction, I'm talking about our ability to actually predict things in advance, not just describe them, not just take some experimental results and then do some simulations on top of that helps inform a hypothesis and maybe describes it. I'm talking about actually predicting in advance. So if you look back at computational methods development, it's been an extremely slow and hard-earned ability to predict something. So we look through big breakthroughs in electronic structure approximations that allowed us to push that frontier further, our ability to do molecular dynamics simulations accurately with better force fields, better sampling techniques. We're talking about decades-long developments. And then if I look at the past 5 years, that prediction frontier has moved at a shocking pace. Can we predict protein structures from sequence? For broad spectra of proteins, yes. That's shocking. We can now do it. We can predict this. Can we predict polymer function from sequence? In some situations, yes. Can we predict, right? So we've seen a lot of aspirational predictions about mappings that we're trying to learn, and I think that we live in a really exciting time because that prediction frontier is moving very quickly. So I'm going to share, as Charles said, we're a methods development group. That's really fundamentally what we do. So I'm going to share some of the methods that we're developing and how I think they fit into this question of where is the prediction frontier. So I would say the most mature area, I wouldn't say solved, but the most mature area is forward prediction. So this is training classifiers and regressors for new properties. Going from structure, whether it's a molecular structure, polymer repeat unit, geometry, crystal structure, to properties, we're getting very, very good at training regressors. There's still a lot to do in terms of training more efficient regressors. How do you train things under extreme data scarcity and things like that? But I would say that this is by far the most mature area. The second frontier is in inverse design problems or inverse prediction problems. So this is going from a set of properties back towards materials and molecules. And this is more challenging because it's learning a distribution. It's not typically one-to-one like a molecule to property mapping is. This is a property to a distribution of molecules mapping. It's a more intrinsically more challenging problem. We are making progress there as well. The third paradigm is property to property. So has this guy gone crazy? There's not even any molecules in this one. We're just going from properties to other properties. I think that this is a really exciting area in terms of this has classically been known as the imputation problem or data fusion problem or data corruption problem. And I think that really exciting things are happening here now for the first time in a long time. Okay, so my talk is kind of organized around these three. I'm going to start with reaction prediction because I think that this is the most challenging forward prediction task we currently have. So my group spent about 4 years developing what I would argue is one of the state-of-the-art methods for doing physics-based reaction prediction. So we have a physics-based approach that I'm going to describe to you briefly, and then I'm going to describe some of the machine learning that we're building on top of that. So the reaction prediction problem is not the A goes to B problem. So A goes to B is you already know the reactant and the product and you're trying to find a transition state. The reaction prediction problem is the A goes to question mark problem. So someone just gives you the reactant side of the arrow, Maybe they tell you what's in the beaker, and they tell you the conditions, maybe what's on top of the arrow. And the question is, what happens? What would it take to do the digital analog of a benchtop reaction trial? So we started that problem with this simple fruit fly, 3-hydroperoxypropanol, asking the question, what happens first as I heat this molecule up? Right? So everyone in here can sort of generate their hypotheses about what happens first. You can look at the structure. You can try to identify what the weakest bond is, maybe. This is what motivated us at the beginning. Now, this is not a talk about our physics-based method, so I'm going to move through this quickly, but the physics-based method that we've developed is this thing called YARP, yet another reaction program. And what we do with YARP is we turn the A goes to question mark problem into a bunch of these A goes to B problems. So we try to enumerate as many hypothetical products as we can in a pretty indiscriminate, generic way, and then we use transition state searches that we've worked really, really hard at making robust and accurate and fast. We use those to tell us what we think is going to happen first. Okay? And then you can do that recursively, and you can generate the reactions. So this is what it looks like in practice. We have these reaction rules that are all expressible in terms of these things called bond electron matrices. So if you want to hypothesize alternative products, you generate a bunch of these reaction matrices. This corresponds to the breaking and forming of bonds, and then you can take those reactant product pairs and you can converge them. So let me just show you what it looks like. So if I were to do all break 2 form 2 chemistry, which is kind of like polar organic chemistry, if I were to do all break 2 form 2 chemistry on this molecule, removing fused rings, here are hypothetical products that can come out. Okay? And you might say, okay, Brett, some of these are silly. It's a high temperature reaction. Are you really going to form a small fused ring or a small ring? Let's filter out small rings. This is what you're left with. Okay, so if you had a hypothesis about what happens, it should be probably in here. And then we do transition state searches on all of them. Okay, we converge activation energies for all of these transformations, and we let that tell us what is the most likely thing that happens first. So if you look at the lowest barrier reaction, it's this, by about 10 kcal per mole. This cyclization of the peroxide, so we thought that a mistake had happened here. So really, is this really the lowest barrier thing that happens first? So the peroxide cleavage is about 10 kcal per mole higher in energy if you wanted to just break that bond. So this is actually known as the Korsack mechanism. So we had no idea about this. This is known as the Korsack mechanism. It's now sort of the accepted mechanism for explaining some downstream products. And so YARP, I think, is good enough to be able to predict this, even for a bunch of people who didn't know anything about this chemistry. And we can now generate really big reaction networks. So I'm going to show you an example here for D-glucose. So can we take this and do this recursively, not just one-step chemistry? Can we actually generate really big reaction networks? So this is D-glucose. So if you react D-glucose using YARP, this is not using any experimental data, you get these sort of, I'm only showing the low barrier stuff. So this is all the relatively low barrier stuff. This ring opening right here is strongly preferred. So you can explore off of that, you can explore off of those, you can start to see things are folding back on each other, so you're discovering alternative pathways to these things. You can explore off of those and explore 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 and explore. So this is entirely generated using YARP automatically without any experimental data. It's the first reaction network that self-consistently explains the formation of the 6 high mass yields that you get out of pyrolysis of glucose. All of them are in this network. They're highlighted in green here. I would argue that we now have very compelling tools to generate large volumes of reaction data with high predictive capability. Okay? Now, we've applied this to polymer degradation. So this was a case study that we performed with Jingo May at Purdue. They were trying to understand the stability and instability of 2 competing reaction units. This has been applied to prebiotic chemistry now, trying to identify how you'd form some small organic molecules from some prebiotic precursors. We've applied it to catalysis. We've also applied it recently to battery electrolyte degradation. And case after case, I think we've made really big progress in terms of physics-based, but really, really hard fought, okay? So really, really hard fought building this whole framework to do these transition state searches and make predictions. So let's build some machine learning on top of these physics-based capabilities, okay? So I want to show you an example of how, even beyond what I just showed you with what we spent 3 years of physics-based methods development, now what we've been able to do in 1 year with the assistance of machine learning, okay? So that's the setup here. So we took that capability that we have, YARP, and we wanted to ask the question, can we use this automated prediction capability in order to calculate half-lives of representative molecules and oligomers, and then use that half-life data to train a thermal stability score? Okay? So this top loop here is showing all of that automation. So the top loop is showing how we can go from molecule to then generating a reaction network associated with the thermal degradation of that molecule, and then doing kinetic modeling, and then expanding the network. So the key here is that you expand the network, and you actually don't need a really big network. You only have to expand the network sufficiently to converge the half-life. So that's all possible because of YARP. So we generate a bunch of these half-lives, and then we use that half-life as a stability score for thermal degradation, okay? So the question is, can we avoid all of that mess and just learn directly the chemical structure to thermal stability score mapping without doing all of this really hard YARP-based work, okay? The hypothesis at the beginning here was that this is going to be a really complicated mapping to learn. So we did all this work. About 6 months of this project was data generation, and then the other 6 months was basically writing it up because the machine learning part was ultra fast. So what we found was that this is only limited to alkane chemistry for now. What we found was that it was hard not to learn the mapping. Actually, we even trained really simple random forest models. We thought we were going to have to use graph neural networks like we've had to use in other projects, but even simple models were able to learn the rank ordering of the thermal stabilities basically perfectly. Okay, that's what the top is showing you. We did a bunch of these case studies where we'd only train on a subset, so like a model that's never seen branching, can it still predict the stability of branched molecules and things like that? And the answer was yes. Okay, so it was remarkably transferable. It could even find some non-trivial things, like if you look at the N-alkanes, which it was not directly trained on actually, there's this kinetic, the difference in stability here going from butane to pentane, and it can even pick up these sorts of subtleties. Okay, so then we said, well, let's test it on a much more diverse range of chemistries. So we can get... we collected all of the polymer thermal stability data that we could get, so like the thermal degradation temperature from TGA, and we also grabbed as many sort of medium-sized molecules that we could, so up to like 60 heavy atoms or so. So we grabbed as many as we could find from the literature and said, how does this framework sort of generalize? Okay, bunch of different bonds in there. To train our model, it's expensive to run YARP, relatively expensive to run YARP, so we used an active learning loop where we took a subspace of PubChem, 750,000 molecules, and we'd grab, I don't know, a few thousand at a time based on our uncertainties about their relative stability, and then we calculated half-lives for those. Now, really importantly, we used an approximate scheme for getting those half-lives because it's relatively expensive to get them. So we used RMG, which is a much more approximate method of getting the half-life. Okay. A lot of data here. This preprint just appeared, so I'm giving you sort of fresh stuff. What we were surprised by were two things. So number one is that this learning curve converged very quickly. So this is showing accuracies in these different classes as a function of those active learning iterations. By 4 iterations, which is like, I don't know, 30 or 40,000 molecules or so, it had converged basically completely. If you look at the alkanes, which is this column right here, the alkanes are basically as perfect as they ought to be for these polymers, because there's a lot of uncertainty actually in those TGAs. If you look at repeated measurements and things, they're plus or minus 10 degrees. So about 95% is as good as we really ought to do. As we sample some of that alternative chemistry, things get better, but it actually saturates relatively low, and that's because we have low quality RMG data. So we really need YARP data. YARP's kind of expensive though. The small molecule stuff for the small, medium-sized molecules, the thermal stabilities are all looking really good really quickly. Okay, so it's really a data generation problem. So this mapping turned out to be much easier than I ever would have expected. That the thermal stability, because you've got all of this, unimolecular rearrangements that can happen that can mediate the stability. This seems to be a shockingly learnable mapping, which I would not have anticipated at the beginning. So we really had no purchase on this problem until that. Okay, so let's move on to the next frontier. So how about the inverse problem? So there's two inverse problems I want to tell you about. So the inverse problem is going from properties. These might be, properties of molecules or materials, or they might be spectra, right? So there's a lot of properties you can measure about materials, and you're trying to go back to material. So one of the big problems that we have in degradation is identifying terminal degradants. So if I were to offer the people in this room spectra, and I tell you I have an unknown species and I'm trying to identify it, and here's an IR spectrum for you. Can you identify what this IR corresponds to? Okay. How about if I give you a little more data? How about if I give you an HNMR, right? How about if I give you an EIMS? How about if I tell you what the starting material was? So unknown product, but I give you the starting material. Well, if you're an organic chemist, you tell me now I have sufficient information, right? So the way that you typically would solve one of these problems is you'd use the heuristics you learned from analytical chemistry, and you'd say, I have the starting material, I can see which functional groups are preserved, which ones have changed, how many protons do I have, and you'd be able to deduce what the isolated product was. So we wanted to see if we could make a machine learning architecture that could automate this process, and hopefully go beyond what those heuristics are capable of doing. So not just using the traditional heuristics, but actually using all the data in those spectra. So we developed this mixture of experts type of architecture. So you can think of these as each being kind of like a ChatGPT, so if that's your mental model for what a transformer is. But what we do is we take the inputted reactant information. Sorry, I keep losing the mouse. We take the inputted reactant information and we map that to basically a string. So we're trying to predict part of the chemical graph. And then we also take those spectra and we convert those spectra into predictions for the next part of the graph. And then we let them talk to each other. And they all argue with each other about, okay, I think there's a carbon here. I think there's a ketone here. And they reach a consensus. And then they all agree on that consensus. And they go back and they say, let's predict the next part of the graph. Okay? So that's how it works. So this is multimodal for chemistry. Multimodal, if you're a CS person, multimodal right now means vision and language, but multimodal in chemistry means spectra, properties, scalars, textual information. So how well does it do? Turned out that this was a shockingly easy problem. So we tested this on, again, we know what the reactant information is, but we give it spectra of the product. Okay, so it doesn't know what it's not getting the chemical information of the product, it's only getting the chemical information of the reactant, what you put in there, unknown product. We trained this on the US patent data that has known errors. So the accuracies for all of these are 90% and above. If you give it 10 guesses, that's as good as you really ought to do on this problem. So it's already up against the prediction threshold. You really shouldn't do any better than that because of the known issues with this data. So that really surprised us. So we also challenged the models a little bit and we said, okay, well, what if we start removing data? So in a real situation, you might not be able to take a mass spec of your molecule. It might be too big or something. It doesn't lift off, or an EIMS. And so you might not have, that information available. How does it do if you start randomly dropping information and the performance still basically is very comparable to the fixed inputs? Something that was very interesting to us is we tried to lie to it. So we said, what if we give it 2 out of the 3 spectra correspond to starting material, and then only the third spectrum corresponds to the real product? And this architecture is actually very robust because the accuracy does decrease, but it recognizes that it's getting signal from so it will decode, if you give it like 10 guesses, it'll decode the contradictory product and the main product that it's getting signal from. So it's a very interesting because it has extra information, more than it needs, it can still actually decode both, even though it wasn't trained to do that. Okay, how about the harder problem? The harder problem is, what if I don't know what the reactant was? What if you just give me the spectra? Is this solvable? What do you think? Marty? But if you just have an IR, is that enough information to predict a chemical structure? The IR? Just the IR. Patterns, yeah, with enough patterns. So the great thing in machine learning is you can try it, right? So we can try it. So this is what you get if you train the models only on the individual spectral sources. So if I just give it IR, if I just give it HNMR, if I just give it EIMS, I have to qualify the mass spec is simulated. All of these are simulated for now, and the mass spec simulator is horrible. So I don't think this reflects the true information in a mass spec, in an EIMS. I think that this reflects the insufficiency of the predictor. However, IR, if it's a small molecule, it will get the top one decoding of an unseen molecule that it was not trained on the order of 65% of the time. It will identify it right away. If you give it 10 guesses, it'll be about 90% of the time. Okay? So that's interesting, right? Because IR, I mean, if you just think of all the constitutional isomer, IR we typically think of as just giving you the subgraphs of which functional groups are present, not how they're connected to each other. It's really interesting that it's actually able to predict it most of the time for smaller molecules. And then it decays as you go to bigger molecules. Well, what if we start combining these things? So if I give it an IR and the HNMR, it gets better. And if I give it all three, it gets even better. And if I pull out all the tricks and I do an ensemble model, it gets even better. So it can identify small molecules. It can generate useful hypotheses for sure about what it is for anything with 10 heavy atoms or less without knowing anything. Okay, without knowing anything about what you started with. I think that's pretty impressive. How does it work on real experimental data? So we only train these on simulated data. And if you compare that with, we got experimental spectra from NIST without any fine tuning, you get a little bit of an accuracy drop, but still remarkably preserves the accuracy without any fine tuning. So we could do better than this if we fine tuned it, but the transferability is really, really impressive. We can also look at what is it learning. Okay, so what is it learning? So we can drop part or mask part of the input spectra and ask if it changes the prediction, and that can tell us what information is the model using to make those predictions. So I'm just going to skip through that quickly. It's actually using all of the spectra pretty reliably. It's also realizing that mass spec is basically useless because these are simulated mass spec. It recognizes it's not a super useful information source, but it does recognize that it's giving it a strong molecular size. So mass spec is very decisive on the last token. So basically the mass spec is quiet until it's the end of the molecule, and the mass spec is like, stop. You've reached the molecular weight, so you can stop decoding the graph. Okay, so it's already piecing together what's useful, what's not. If I look at what's decisive for what, you can see that some of these characteristic stretches are IR decisive. The HNMR is decisive for a lot of the alkylic units, so it's reproducing kind of some of our intuition. You can even look at the individual spectra and identify which peaks are decisive for which decodings, and it matches to how you'd interpret a lot of these spectra. So here's the HNMR decisiveness, here's an IR decisiveness, so the typical heuristics associated with IR, it's sort of recovering those. Even mass spec, this one is quite interesting. If you look at the first chloride or the first chlorine, it uses a different part of the spectrum than another because there's a typical, I guess I don't know this, but analytical chemists if you have multiple chlorines, there's a characteristic pattern associated with the second one because of the isotope proportions. So this is like a well-known heuristic, I guess. So I'm very optimistic about automatically determining chemical structures from spectra. The second one is, how about designing molecules from properties? So instead of spectra, what if I just want to put in molecular properties and predict molecules? So, okay, good. I still have about 10 minutes. So right now, the holy grail is you give me properties, I give you the molecules that satisfy them perfectly. Okay, or I give you the polymer repeat unit that will satisfy that perfectly. That's the holy grail of design. Now, the issue with the way that this is conventionally approached, and we heard some of this yesterday, is that it's extremely challenging with conventional architectures to do inverse design for multiple properties simultaneously. And that's because the conditional distribution becomes sparse very quickly as you start saying, I want to constrain the molecular size, I want to constrain which functional groups I have, I want to make sure it's synthesizable, I want to make sure that it's soluble, I want to make sure that it has a band gap of this, I want to make sure that it has a oxidation, right? So as you start to add things up, it becomes very difficult to constrain all of these at the same time. Now, a couple observations. So in conventional architectures, what you do is you try to learn the mapping of a graph given, so a chemical graph, chemical structure, given a property. But the thing is that every molecule or material you make doesn't just have that one property. It has all these other properties, right? It has all those other things I listed. And when you are asking someone for a design, when you come to me and say, hey, Brett, can you help us design this material? We really want this activation energy, or we really want this, binding energy with this enzyme or something. You're also simultaneously saying to me, I want it to be stable. I don't want it to be too big. I also want all these other things to just be normalized. Draw them from a reasonable physical distribution. That's really what you're saying, right? Normalize all those other things and just give me a couple of the properties that I care about. So our idea was, well, instead of just training it against your one property, which is often very data scarce, what if we trained a general model that had as many properties as we could throw at it? A bunch of mundane properties. Because those properties are still very informative about the physical distribution of molecules. Those will help situate you in a space of reasonable looking molecules and will help regularize your predictions. The other observation is that conditional distribution of molecules that match properties, it simplifies as you add more properties. So here's a question for the audience. How many properties does it take to uniquely define a chemical structure? So I give you a band gap. Band gap's not enough. Surely there's many molecules have the same band gap. Okay, what if I also give you a solubility, a partition coefficient, a thermal stability, a dipole moment, a quadrupole moment? How many properties do I have to give you until you get down to a unique chemical structure? Eventually, this will become a delta distribution, and there will just be isolated molecules as you give it more and more properties. So the mapping becomes easier the more properties you give it. So we tested out this idea, we call it a large property model, and we started just trying to learn how many properties do I have to give my transformer until I can directly decode the chemical structures that map to that property vector. Okay, this is the architecture. I'm just gonna skip over it a little bit. So what does property space say? So I can take a bunch of molecules and I can see how they're distributed in property space. So what we did is we took 1.2 million molecules. We've now scaled this up to 15 million molecules from PubChem, and we calculated 22 properties for all of them. And then we said, how clustered are they in space? Okay, so if I just distribute them in space, how clustered are they? So we find that the molecules are about 5 times more clustered than random distributions of properties would say. So that's already signaling to us that the physical manifold of molecules doesn't occupy the full property space. There's a physical manifold that's a subspace of that larger space. The other thing that, I could not have predicted this. This is the nearest neighbor separation as we increase the size of the heavy atoms. So in other words, more molecules are getting dumped into the space as I go to the right of this plot. At all of these separations, the molecules are all distinguishable in property space with respect to at least 1% of one property. So you might say to yourself, you only gave it 22 properties. They're surely going to be sitting on top of each other. But they're not. 22 properties is already sufficient to distinguish all 1.2 million of these molecules in property space. They don't sit right on top of each other. If you look at how many properties do you need, so you need about 10 or so properties until they're sufficiently distinguishable, or on average distinguishable from one another in this space. It's kind of interesting. We had no assumptions about this going into it. That means it should be learnable. If they're distinguishable in property space, then the property to chemical structure mapping should be learnable. And this is our initial demonstration of this. So we train that mapping. If we just give it the properties, it can decode the molecule that corresponds to that property vector that it's never seen before about 35% of the time. Which is astonishing because, I mean, the number of hypothetical molecules that might map to that property vector you'd think is basically infinite, and it can identify 35% of the time the molecule that generated that property vector. If you give it 10 guesses, it goes much higher. If you just look at does it match the formula, it goes even higher. It basically never gives invalid molecules, and it generates tons of new molecules that when we test it have matching properties. So it's spitting out many options of molecules that have the properties graph. So I think that this is a really exciting paradigm for molecular design. What we're looking at now, and I'm hoping, have postdocs who will maybe work on this in the near future, is now that we have this big property space, can we fine-tune this on data-scarce properties and generate molecules conditionally on data-scarce properties that we care about? I'm really optimistic about that. Last thing I want to tell you about in just a couple of minutes is a very new project, so I don't have too much about it, but this is the question about property imputation. So most property databases are really sparse. So you've got, if you think about the column, all the columns of all the possible properties that you have, and if you're at a pharmaceutical company, you might have some properties for some molecules, other properties for other molecules. You might have the same property measured with different instruments. So property databases tend to be very sparse. So the question is, can we train a model that leverages the properties that are available to impute the properties that are missing? So the vision that we have is that you bring your data to us and you dump in a sparse database and out comes a dense database on the other side. Or a nearly identical task is you pass us a corrupted database that has a lot of uncertainty in values, and it decorrupts the values and it identifies the outliers, because what we learned in the last part of the talk is that the properties have mutual information. So if I have 9 out of 10 properties that say one thing, and then you did a digit transposition on that 10th property, this model can figure that out. It can identify you did some kind of digit transposition. It needs to be decorrupted. Doesn't fit with the other 9 properties. So we've trained a model like this. I'm just going to show you some of the early results here. So it's using that same data set that we had for the large property model, so the 20 or so electronic structure properties that we derived. And this is what happens when you start randomly dropping properties and trying to fill in the missing properties. So the green here means that the R-squareds are all pretty good, so we're actually able to impute the missing properties. Even with 4, 6, 10 properties removed, we're still getting quite robust property imputation on the missing properties. If you look at how it's using information, so this metric is just how does the R-squared shift if a property is missing. Some things are highly correlated, like the HOMO-LUMO gap, the ionization potential, and the electron affinity. Those are mutually related. If you know 2, you know the third. So there are some obvious mutual dependencies, but by and large, it's actually using very diffuse reasoning across all properties to predict the unknown properties. So it's very interesting that it's using broad-based information sources to do that. And then the last thing I want to show you is that imputation task that I just showed you, that's the hardest task because we didn't give it any chemical structure. We just gave it the properties and asked it to impute the missing properties. But for chemical databases and materials databases, you know the structure, even when you don't know the properties. So what if we give it the smiles? Oh man, I can't find, there it is, okay. What if we give it the smiles and the missing property, and the incomplete property vector? How does it do? And you can see it gets much greener, okay, going from here to here. So adding the additional property, or adding the molecular structure, increases the predictability even higher. And if you compare these with the basic regressors, if you were to just train a direct property regressor for each of these individual properties, it'd be way below even this baseline over here on the left, okay? So I think it's a very exciting direction. We're hoping to put together something that will hopefully be published soon. I'm giving you the early treatment here. So this is a bit of a dated photo. So this is back when I was still at Purdue. About a year ago, we took this picture, but a good chunk of the people who did this work are in this picture. So I want to call out in particular, so Chuan Zhao there on the right, he actually led the development of YARP. So all of that hard physics-based modeling that we've now been building a lot of our machine learning on top of. Tianfan led, right next to Chuan, Tianfan led the structure prediction stuff, and Drew there on the very left, Drew's leading that property imputation and data fusion modeling. And I'd be really happy to spend the next few minutes answering questions. Thank you.
Yeah, Brett, fantastic talk. I want more because so amazing. So I have two questions. The first one is related to using the spectrum, using the plots to predict the molecular structure.
Yep.
I'm asking fundamentally, is it possible to predict polymer, to describe polymer? If so, what's on your wish list from experimentalists to provide to you? So the second question is related to property prediction. So we know that if you have a pretty smooth surface in terms of prediction, well, that's kind of straightforward. But for property, a lot of time, the amazing property comes from transient structure, from sparks. Is your model will be suitable for that one?
Yeah,
Thank
so
you.
both excellent questions. So the really exciting thing about, so first the structure prediction. So I introduced this whole thing with, can you predict it? I put Marty on the spot. Can you predict the structure from the spectrum? And there's actually no good information metrics to tell you whether or not something is predictable from a given spectrum. So your question about what would it take to be predictive for polymers is, I don't think anyone actually knows the question about, what is a sufficient basis set of characterizations that will uniquely determine what you want about a polymer. Now, if you only want to know something probabilistic, like a distribution, if you don't need to know the exact sequence, you just need to know probabilistically if it's an alternating polymer or something, what's the proportions, you probably need less information than you do if you want to know higher order moments or things like that. So I don't think fundamentally, though, this architecture is completely input agnostic. So we could extend this to 10 different spectral inputs if we had the data. We could extend it to also a mixture of simulated inputs and analytical inputs. I think that's an exciting, especially for if you had some molecular simulations that could at least falsify some hypotheses, and then you have a small number of experimental characterizations, I might be pretty optimistic about. So then the second thing was, you said about transient structures. So I actually cut all of it from the talk, but we've been using a lot of, we've been developing graph neural network architectures to predict activation energies, which is a transient structure problem, right? So you're trying to infer something about, from just knowing the graphs of the reactants, or reactants and products, you're trying to infer what does the transition state look like, how high is it in energy compared to the low energy, and within distribution, so if you've seen examples of that reaction class, you can get within a couple of kcals per mole. So but you need an example of the reaction class. If you're out of class, you can get really terrible accuracy. Yep.
Oh yeah, so in the larger property model, you mentioned kind of 22 properties are enough to make singular molecular prediction. I wonder, how did you choose those 22 properties? Are they just diversely sampled, or how did you choose that 22 properties?
Yeah, the 22 properties were sampled entirely by convenience. So they were the things that we could calculate using semi-empirical electronic structure methods. So we would love to diversify the properties we look at, but we just basically got everything that was possible using semi-empirical electronic structure. And then we're now extending it also with some regressors. So like machine learned properties. So we can also augment it with some additional estimated properties too. But yeah, it's entirely just opportunistic.
Thank you.
Yeah.
I just wanted to ask you a little bit of extension of your work. Can you use this modeling technique to increase the sensitivity and accuracy of Raman spectra, for example?
I'm extremely optimistic about two things. So one is we know from image generation that you can do super resolution. You can upscale images very well, right? So machine learning is very good at learning how to upscale something using a low resolution example, as long as it has a similar distribution to your training data. So I'm really optimistic about taking low quality analysis, like if you were doing X-ray or something, if you want to do a low dose X-ray, so try not to damage the thing, but still get high resolution information. I think machine learning could actually upscale a lot of our spectroscopies and things. I think the second thing you were saying, though, is about how much we can get out of the spectra. And I think that's unequivocally demonstrated here. I think these models can extract way more from these spectra than the simple heuristics do. I think that's demonstrated.
Thank you.
Hey, Brett, totally fascinating talk. I got 3 quick questions. So, how much better do you think the property imputation could get if all the molecules came from a bounded set of blocks? For example, you mentioned AlphaFold. It's 20 blocks in sequences. Yep. That's why those patterns emerge. So given what you've done with that unbounded set, really, without any selective pressure around the chemical space, how much better do you think the imputation could be if you actually intentionally start with bounded block sets that make all the molecules?
That's right. I think that actually... I think you could do arbitrarily good. I think that might even be the biggest advantage of having a well-delineated chemical space, is that you can actually sample it completely. You have no surprises, and so many of our properties are sort of decomposable. So you get to these theoretical spaces that are really huge, but you get that with a product of combinations. Yep. And you just really need the pairwise and maybe second-order relationships, and they're highly predictive.
And is that why all life is modular? I think there's a connection there to fundamental basis for evolution, its capacity to happen in the first place, because evolution is really picking up these same patterns, but just through the process of natural selection. So I think there's something deeply fundamental about what you just said.
That's an interesting...
How much better could imputation get if you don't just look backwards into a data set, but could actually do active learning to fill in the blanks in an intentional way with smart choices about where to sample?
Exactly. So this actually kind of ties together the first couple of questions. So the underlying hypothesis between both of the property prediction, the molecular property to molecule prediction and this imputation is that you only need so many properties. Even mundane properties have information about the data scarce. We think of them as really prized properties. And so what we were trying to get at with this here was which properties are the most informative, right? So are there 10 properties that are just golden? They're orthogonal to each other. They provide fully complementary information. That's all you need to predict everything else. We're still searching for that. But I do think you don't want to waste your time collecting 3 correlated properties. You want to actually get this sort of... I'm a theorist. I think of basis sets. You want a basis set of properties.
Okay, very interesting, which actually is another path to get to what are the basis set of blocks from which you could create all small molecule function, kind of analogous to canonical amino acids. This is something we've been thinking a lot about.
Yeah.
Okay, last one. Do you think that these cross terms that you're picking up in terms of interdependencies in the imputation exercise, this is a fundamentally new way to do basic science because you're picking up the fundamental drivers of those cross terms. I mean, we saw this in the OPV project, in which if you pick up R squareds that are surprising between some type of fundamental, physical organic chemistry property and the objective function that you're interested in, that's telling us something, right, about the fundamental drivers of that property. So do you think if you take a step back and imagine kind of doing this on scale, it's a different way to understand how physics intersect with chemical properties?
I completely agree. So it's even more than the imputation. I think when we look at the molecular generation, the proposals that are coming out of these can oftentimes be really counterintuitive about how it's navigating these trade-offs between satisfying these different properties. And then it's only by looking at them that we learn something new. We say, oh, that's actually a new design strategy that we didn't know. But my take on this right now, at least, is it's very much human in the loop, getting eyes on these things. I think it's an open question of if you could do these loops and get an AI to look at them and make a simple reasoned argument about a structure-function relationship. I think that's where the frontier might be.
Awesome. Thanks.